Hello everyone, my name is Sebastian Chavez, Associate Researcher from the University of Campinas. And today I'm going to present you a resource entitled Transient Switching Analysis of a Non-Conventional Rural Generation System. The co-author is Professor Dr. Maria Cristina Tavares, and this paper presents a method to electrify small communities using a collector line located into the railway of the high voltage transmission line and analyze the response for some switchings. So my research was focused on proposing a method to supply electricity to small villas that are located close to high voltage transmission line. Some villas and small communities are in the vicinity of the transmission line. However, they don't have electricity due to the small size of the electrical load. So in these cases, the use of conventional methods is economically infeasible. So electrification methods became an engineering challenge for this kind of projects. So previous literature solution proposed a modification of the transmission line assets, which is a major concern to power utility companies. In order to overcome this problem, we propose the construction of a collector line composed of an asset of parallel insulated wires within the transmission line railway. This alternative increases the generation source cost, but does not compromise the transmission asset and can be installed near existing transmission lines. A single-phase generation system is obtained as I will present you now. So, including a collector line into the railway of the transmission line, we get this equivalent. However, this system has a low voltage regulation due to the high impedance of the internal source. So, a series unit reactor with the same reactance value that the source equivalent capacitance is included in the system. This creates a resonant circuit which entails a maximum energy transfer. As a result of the resonance circuit, the voltage on the collector line increases as the load increases due to the branch current. So, position the collector wires that are actually floating wires is not a straightforward procedure. The optimum position must attain some restrictions and objectives. In this way, the position of the collector line was obtained by solving an optimization problem related to maximizing the induced voltage, minimizing the tuning reactor, and minimizing the assembly costs subjected to the following constraints. Transmission line shielding wires should shield collector line from lighting. The collector line height can be higher than phases wire height. The collector line must not be under phase conductors, and the collector line height must respect the minimal distance to the ground at minimal span. And finally, no corona effect must be created. So a genetic algorithm was used to optimize the allocation method, allowing the designer to have the final decision. So consider a 230 kilovolts host transmission line. The voltage coupled on the collector line is 13 kilovolts at no load condition and goes to 40 kilovolts line to ground when attending the target load, what corresponds to a 69 line to line. Our target load is 100 kilowatts. So the chosen solution corresponds to a bundled wire with two floating conductors with electrical characteristics of regular shielding wires. A sack of 8 meters, a tower height of 15 meters and 30 meters to distance to the center of the transmission line. So this collector line geometry was used in the entire resource. So this is the power system configuration used to simulate other cases. The 230 kilovolt transmission line has 200 kilometer length, right? The system is composed to two equivalent systems: the transmission line, the actual transportation towers, shunt compensation, and a ground resistivity of 4,000 ohms meter. The 20 kilometer collector line goes from the kilometer 100 to 120 with a common point coupling at 110 kilometers, what we identify as PCC. Once the collector line was set, it is necessary to define the best topology of the capacitive coupling system to harness the maximum possible energy from the host transmission line. The CCS proposed is based on the use of a transformer group. The first transformer, T1, is connected directly to the collector line to reduce the tuning reactive value. A second transformer, T2, converts the voltage to distribution high voltage level, allowing the use of conventional elements. For this study, a voltage of 20 kV phase to ground was considered. Imposed the transformer voltage T3 as 20 kV to 110 volts. Considering the target load, all the transformer capacity is set as 120 kV. Also, the transformer radio for T1 is set as 5. So now it's necessary to identify the voltage of the collector line. So we have base topology considering just the tuning reactor, the feeder, and the 100 kW load. In this case, the collector line voltage is around 42 kilovolts. With this, we can define the nominal voltage of the transformer T1 and T2. So in this case, the actual collector line voltage is around 39 kilovolts. So the tuning reactor is calculated considering the reactance of the CCS transformers. As you can see, the CCS elements specification depends only on the target load. So to continue the evaluation of the proposal, I consider that the use of this non-conventional system must never compromise the transmission line integrity and reliability, and shall be a safe distribution system as well. A detailed electromagnetic transient study was implemented. The PS card was used to perform the electromagnetic transient studies, and some conditions also were considered. But the host transmission and the rural feeder were represented using the universal line model. The single circuit transmission line has two shielded wires, and the transposition cycles are properly modeled. Only in the collector line region, the transmission line was modeled with the additional collector line bundle located as shown in the figure. Also, we have to consider that due to the transposition, phase A is closer to the collector line. Also, it should be noted that transmission line switching will produce high transient overvoltage along the rural feeder. Therefore, we have installed spark gaps along the collector line. There are places at 0, 10, and 20 kilometers for the collector line. The electric arc in spark gaps was modeled as a breaker connected between the collector line and through the ground. The breakdown voltage is set as 140% of the collector line nominal peak voltage for the target load. That was set to 8 kilovolts. So to start the transient analysis, the host transmission line energization was simulated. In this case, the sending breaker is closed in a flat random time along a cycle when the breaker at the beginning of the feeder is already closed. After a statistical study using 100 simulation, the results show that there is not significant overvoltage on the collector line and neither on the tuning reactor. Meanwhile, the rural load presents a minimal increase even in the worst case. Here in the right side, we can see a deterministic case of this study. It is evident how the low voltage quality is very high, with harmonic content near to zero and no important overvoltage observed. It's also important to highlight that the transient response at the feeder is quickly attenuated due to the capacitive circuit response. The transmission line load trip was simulated considering a statistical open switch with an uniform distribution over a cycle using 100 shots. After the dead time, the sending circuit breaker was open. Results showed that the overvoltage increased at the rural system. The most severe entity is the voltage across the tuning reactor. Let's see the deterministic work case. So the receiving breaker opens, then a 1 point PO overvoltage appears along the transmission line. Then the induced voltage at the collector line rises properly until they overcome the spark gap's breakout voltage. In this short time, tuning reactor voltage rises fast, reaching 2 pu. Spark gaps operation reduce overvoltage almost immediately. Due to their small duration, they do not injure the real system. When the transmission line overvoltage damps, the gap extinguishes, and after that time we can observe the transmission line voltage damping ramp. After 5 cycles, the voltage along the feeder presents a sinusoidal form again. So fault occurrence on the transmission line is a severe condition as the collector line induced voltage can reach very high values. Knowing that the induced voltage depends on the transmission line phase voltage, therefore it is expected that overvoltage on the transmission line will raise the collector line voltage. So a statistical case was implemented considering 6 fault resistant values with 700 shots for each fault value. The fault location was the PCC, obviously in the transmission line side. The fault case consists of applying a fault considered a uniform distribution over a cycle. So the receiving breaker opening after 100 milliseconds, and a cycle later the sending breaker is tripping. So due to the spark gap protection, collector line voltage does not increase drastically. Therefore, the voltage along the rural feeder remains within acceptable levels. As I told you before, the collector line voltage is mainly derived from phase voltage through mutual capacitance. This means that the closest phase has a higher contribution to the induced voltage. Therefore, faults applied at phase fader from the collector line will produce higher overvoltage due to the contribution of the closest healthy phase. Here I present the most severe case regarding rural load overvoltage. It consists of phase BC to ground fault using a 5 ohms fault resistance. After the fault occurs, we see the spark gaps operation continually before the transmission line breaker operation. Once the voltage of the transmission line reduced due to the line protection operation, collector line voltage remain elevated. Then a spark gap at 10 kilometers of the collector line remains on operation over and over again. Once the collector voltage is back to normal level, the rural system goes to normal operation. It can be observed that there was no important overvoltage produced by the transmission line faults at the rural load. Now it's time to evaluate the interference of the CCS to the host transmission line reliability. First, let's see the fault at the collector line. The case characteristics are similar to the previous cases. A 6-fault resistance was analyzed using a statistical study with 100 shots for each fault resistance and uniform distribution over a cycle. The fault was applied at the PCC at the collector line side. So the statistical results showed no variance for overvoltage along the rural feeder. Basically, the collector line was grounded, removing the induced voltage and detuning the resonance circuit. The deterministic case with 0.1 ohms shows the voltage at the rural system is 0 after a fault without any transient overvoltage. In this case, the spark gaps were not activated. However, a small interference on the transmission line voltage can be observed with any important effect, right? Because it's short time and is small amplitude. To conclude, our resource consists of proposing a non-conventional capacitive coupling generation system composed of a collector line and an innovative distribution substation. The energy is extracted from the electric field in the surrounding of the extra high voltage transmission line without any contact with the transient line assets. This generation system can provide fewer energy adequate to attend small off-grid communities and even be considered as a second supply source for a weak rural system. Finally, the system was protected with the spark gaps positioned along the collector line in order to mitigate the overvoltage transient, presenting a great response. The rural system does not compromise the power system reliability and the performance on the host transmission line. So, thank you so much for your attention.